In this section, we will study about properties of Laplace transform. The first one, linearity. We know that Laplace transform is just an integration. Due to that, the linearity are satisfied. The first one, taking the Laplace transform x1t are equals to x1s, and the given region of convergence is R1, and the x2 Laplace transform is x2s, and the region of convergence is R2. Then the Laplace transform of this one, it means the Laplace transform is taken over the sum of this function x1t plus b over x2t b times x2t. Okay, this function is producted by e to the minus st and dt. By taking this integration, we get the Laplace transform of this one. Because of linearity, it's obvious. The second thing we have to consider is the region of convergence. This part to converging, S should satisfy some specific region, and also this part also satisfies some specific condition. That's the R2. So both of them should converge. Due to that, we need the intersection of R1 and R2. So that is the region of convergence of that. For example, the region of convergence for R1, let's give us some of the example. Here is S domain, and R1, for example, should satisfy this side. Okay, that this one is R1 region, and R2 region are like this one, R2 area, right side of this one. Then Laplace transform of this one should be the intersection part of this one. At this moment, the R1 is left-sided. Okay, so R1 signal left-sided one that come from these limitations. At the t goes to minus infinity, it should be it should be converging at that area, and the R2 case is the right-sided area. So in this case, the right-sided signal should converging as time is infinity. It should converge. That's this reason. So to satisfy both conditions, we need to take the intersection of them. The second property is time shifting. By taking the Laplace transform of xt r equals to xs, and the region of convergence is r, then the Laplace transform of the shifted version, that's this one. Time shifted version Laplace transform are defined like that, and just replace this one as a tau. Then this becomes x tau, and t should be equals to tau plus t0. And dt equals to d tau. Okay, then by use of change of variable, we can show that the same integration are given like that. And there is some factor e to the minus st0, that's this part, and xs equals to this part. And the region of convergence for the integration should be the same, because the integration range of this one are the same, so the requirement for the s should be the same. Means that we need to take the integration, this one, x tau times e to the minus s tau d tau. Consider that the requirement for the s are the same as this one, the original Laplace transform. Here is an example. Xt is defined by ut minus tau. There is a time shifted version. Okay, then Laplace transform of unit step is 1 over s. It is a right-sided signal, so region of convergence is a positive side of the s plane. And time shifted version is this one. So the inverse, the Laplace transform are given as 1 over s. That's the unit step, and the time shifting factor are introduced the e to the minus s tau, and the region of convergence are the same. So by taking the Laplace transform of this one by use of the linearity, we can do the things. 1 over s, this part, come from the unit step function, and 1 over s times e to the minus st is this part. That should be subtracted due to these minus signs. Both of these one, the intersection area should be the same as the real part of s is positive. It means that it's the right side is zero. The third property is shifting in S domain. So xt, Laplace transform of xt is given xs, and the region of convergence is R. So in that case, let's assume that the R are given in the S domain for some region like that, R2 and R1, and the region of convergence R are defined. For example, like this is the region of convergence of that. And then we would like to take a Laplace transform of this one, shifted in S domain by taking the inverse, the Laplace transform of this function are given minus infinity to the infinity xt, and times we have s0 over here, e to the minus s minus s0 t dt. Okay, this is the Laplace transform of the exponent s shifting. Okay, then this one are equals to x s minus s0. But for the convergence of this one, real part of this one, real part over s minus s0 should have satisfied R. It should be equals to R. Then the real part of s are equals to R plus real part of s, real part of s0. Okay, this is added. Then region of convergence can be expressed in this way. So it means that it should be added like that. Plus, okay, this one is original region of convergence. Then after shifting this much exponent, the region of convergence are given like this way, plus real part of s0. And here is also real part of s0 are added like that. So this is new region of convergence for shifted signal. Okay. The fourth property is time scaling. Time scaling is like this one, x over 80. So a is a scale factor. In that case, the Laplace transform are defined like that, minus infinity to the infinity x over 80, x over 80, and e to the minus st and dt. Okay, we try to use the change of variable. Let's assume this is tau. Then dt equals to d tau over a, because at are equals to tau, so dt are equals to d tau over a. And if a is positive, then tau will changing from minus infinity to infinity if a is positive. What about a is negative? Then in this case it's infinity, and it goes to the positive infinity t, then it should be approach minus infinity. Okay, the interaction direction depend on the sign of a and b, and a is divided here by replacing dt. Then we can rewrite that one is an absolute value over a, and changing index is minus infinity to the infinity. Okay, that is the idea for this absolute value. So if it is positive, it changing minus infinity to the infinity. If it is negative, the minus sign is come out. That is the absolute sign like that. And then we take the x tau and e to the minus, at this moment t, you know that t equals to tau over a. Okay, so we can replace that one s over a times tau and d tau. Then consider here, that is this Laplace transform. What about the region of convergence? For example, the original function region of convergence are defined similar to previous one, that this one is R2 and this one is R1, and let this one is a region of convergence of the original Laplace transform. And then you know what, to converging, the real part of this one should satisfy these conditions. So let this one is R, then real part of S over A should include inside of R. So it should be, actually it should be equals to this area, this region. Then the real part of A, real part of S should be equals to A times R. Okay, it should be A times R. So this one corresponding to region of convergence should be equals to A times R. The meaning is this one: if A is positive, then A and A are multiplied here. What about A is negative? If A is negative, then the sign will be changed. This should be A times R2, and this should be A times R1. So this should be the region of convergence. So when the A is negative case, in case of A is positive, it may be the same. That is if expressed by A times R. So we talk about how we converting the time-scaled version. And here you need to keep in mind this A, I replace the 1 over A absolute value and x over s over A. Okay, this one is the time scaling factor. The fifth one are the conjugate functions. Okay, xt satisfy these conditions, and then what about the Laplace transform of x conjugate t? Then it is defined in such a way: x conjugate times e to the minus st times dt, and then this conjugate function can be drawn out at here, and we attach the conjugate s over here. Then this part equals to xs conjugate, and another conjugate is added here. And the region of convergence related to the real part of s, so it doesn't matter with the conjugate value. Even we take the conjugate, the real part are the same, so the region of convergence doesn't change. What if the x is real? It means that the conjugate xt equals to xt. Then it should be the same. So it should be the same like that. So it says that the x over s equals to x conjugate over s conjugate. So this satisfied when xt is a real number. The next property is convolution. x1 Laplace transform is x1 over s, and the region of convergence are defined R1. And Laplace transform of x2 is x2 over s, and the region of convergence given as R2. And then what about the convolution of x1 and x2? We take the Laplace transform of x1 convolution x2. Then the convolution is defined in this way, and we take the Laplace transform of this one. Then we take the convolution over tau, okay, and Laplace transform is taken over t, okay. Then we can integrate that one into this way. Here is x1 tau and e to the minus s tau. You know what, at here t minus tau is replaced by t prime, okay, at here. Then we can replace this one as a t prime, and in that case is t equals to t prime times t prime plus tau. Okay, then this exponent will be given in this way, x1 tau and x2 t prime e to the, you need to replace t like that. Then this one is s tau and e to the minus st prime, and d tau, you know what, dt equals to dt prime, so we take the dt prime. Then tau integration is x1 tau e to the s tau and d tau, that's this part. And we just replaced this t prime with a tau. You can still use a t prime at here. Then x2 t prime is this part, and e to the minus st prime is e to the minus s tau. We take the derivative, we take the integration over minus infinity to infinity like that. Then is a product of the two Laplace transform, but both of them should converge in the region of convergence. To satisfy that one, the final region of convergence is the intersection point of these R1 and R2. Okay. The next property is a differentiation in time domain. So inverse Laplace transform of xt is defined like that. This one is definition of inverse Laplace transform. From here we take the derivative with respect to time. Okay. Then we take the derivative with respect to time. Then s will come out. So this is the time derivative terms. So xt has a xs Laplace transform shapes. Then dx of dt should have sxs. Okay, so the time derivative Laplace transform is s times original Laplace transform. So from here we can understand d of dt operator are equals to s in Laplace domain. This time the region of convergence doesn't change. It means that the region of convergence are the same as the original region of convergence. What about the differentiation now in S domain? We talk about the differentiation in time domain, but at here we would like to consider S domain differentiation. Okay, Laplace transform is defined in such a way, and region of convergence is defined as R. And by taking derivative with respect to S, so this one shows that the S domain derivative. In that case, by taking derivative with respect to S, then minus t will come out. Okay, then from here we know that the Laplace transform over minus t times xt becomes it's a derivative of ds. It means that the Laplace transform of minus t times xt equals to dx of ds. Region of convergence at this moment, it doesn't change, it's the same. So we talk about the two differentiation. One is in time domain differentiation, and the other one is the S domain. And both of them cases, the convergence requirement for the e to the st doesn't change. So the region of convergence are the same for the original Laplace transform. The next one is the integration in time domain. We assume that the xt Laplace transform is xs, and the region of convergence are R equals to R. At here that the integration are defined in this way: x tau times d tau, tau changing minus infinity to t. This one equals to convolution of xt and ut. As we talk about in convolution operation, if time domain convolution, you know what, the integration operator are the same as the convolution between unit step and xt. So by taking convolution in the time domain, in the Laplace transform is the product of that. It means that the Laplace transform over ut is 1 over s, and the Laplace transform of xt is xs, and the product is the actual Laplace transform of this function. and we know that both of them should be converging in the region of convergence. So we need to find out the region of convergence are defined in this way. You know that we assume that region of convergence for xs is R, and the region of convergence for the unit step are real part of s is positive. So we need to find out intersection of these two regions. For example, if S domain region of convergence for R is defined in this way, let this one is R2 and this one is R1 and this one is 0, then this part region of convergence for the unit step is defined the positive area. So the intersection point is this one, R, and real part of S should be positive. So satisfy both conditions, the region of convergence for the integration are given like that. So region of convergence and the Laplace transform shapes are given that way. And next, consider for initial and final value theorem. We assume that xt is 0 at t is less than time at t equals 0. So we only consider after t is positive condition. Okay. We would like to find out the initial value at t equals 0 and would like to find at the final value as t goes infinity in S domain. To find out the initial and final value in S domain, we would like to consider this integration. In fact, this one calculate the Laplace transform of time derivative component. We take the integration from 0 to the infinity because xt is 0 if t is less than 0, so signal exists only positive time. Okay, we would like to use the integral by part. First, we take this one at here and take a derivative part is integrated like that, and the integration range from 0 to the infinity. That's this one, and the minus the integral part is the same like that. Integrate part, take them here, and we need to take the derivative this part, then minus s will come out, but the minus subtraction signs will be cancelled each other. It becomes a positive. You know what that when we take the f prime g dt will be equals to f g, and take integration, for example, a to the b, then a to the b, and the minus integral. This part is the same, and the g should be taking derivative and dt and a over b. This is integral part by part definition. We use the same thing over here. Then this part is the Laplace transform of xt, so that's why it is given like that, and infinity is entered here. It's a converging in the region of convergence, so only x0 are remained here. And by use of these equations, we can find out real and final value. Let's consider how to find out the final value theorem. From these integrations, we know that when we take the s goes to the 0 limit, then this becomes to 1. Okay. Then by taking integration of dx of dt over time, then it will give x infinity minus x0. And also we know that the Laplace transform of this one equals like that. So we take the s goes to the 0 from here, and minus x and minus x0 will cancel out. So the final value are given like that. So this one is called the final value theorem. The initial value theorem are shown here. When we consider when s goes to the infinity, then due to the convergence property of this one, it should approach to 0 as s goes to the infinity. And when we know that the integration of this one should be equals to this value, so as s goes to the infinity, it should be 0. So that's why x0 are equals to this value. This is called the initial value theorem. By use of initial and final value theory, we can find out the time domain infinity case and the initial value in the S domain by use this one. So here shows an example. xt is a right-sided signal, and if t is less than 0, there is no signals that exist. And we would like to find out the initial and final value for the given Laplace transform of x. The initial value can be found by these techniques. After multiply s over here, s times xs, and take the s as infinity, then this one is s cube and 2 times s cube, and the other part will finally cancel out by taking this limit. Then this becomes the 2. That should be equals the initial value. So at t equals 0, it should be 2. What about time goes to infinity? xt will approach certain value. So to find out then that one, we need to use this approach. Multiply s over here, then after that, taking the s goes to 0, then we have s 2s square plus 12, and over s cube, and something like that, and 20. If we taking s approach to the 0, then denominator remains only 20. Okay, only 20. But numerator approach to 0 because of this s. That's why the final value are 0 in this case. So, use of initial and final value theory, we can find out the initial value of the xt and the final value of the x infinity as t goes to infinity. So the initial and final value corresponding to time domain value. How are we going to apply that one? That's the key idea for the initial and final value theorem.